Right, so good afternoon and welcome everybody. My name is Simon Ritter. I am the Deputy CTO at Azul. And as I said, the idea behind this workshop is to talk about modern Java. And the way that I've kind of structured it is we'll talk about everything that's really changed. I was going to focus on everything that's changed since JDK 11 through to JDK 17, but I've actually included some of JDK 10 as well, because there's one particular feature that was added there, which is local variable type inference. And that's actually something that's worth spending a little bit of time on to understand how to use that in the best possible way. Right, so if we get started with this, sorry, I'm just going to. Right, so if we get started, let's talk a little bit about Java in 2021. What is Java like at the moment? Well, the first thing is that Java is what we can consider a mature language, and it's one that's been around for 26 years. 1995 was when Java was first launched. I actually joined Sun in 1996, about 8 or 9 months after Java was first released. And what's really impressive about Java is the fact that it has consistently been in the top 3 most popular languages. It's really maintain that level of popularity in a quite incredible way. And I think if you look at the language itself, yes, it's a very good language. It's used a lot by developers. It can. Okay. Is that better? Okay, hold on. How's that? Okay. So yes, the language itself is very useful. It can be applied to many different types of applications. But I think the thing that really makes Java as a platform very popular and very powerful is the Java virtual machine. The fact that you're running on the managed environment of the JVM and all of the things that JVM can do in terms of automatic memory management, it does garbage collection for you. But really, kind of the most powerful thing there is just-in-time compilation. The fact that you can compile code as your application is running and get the best possible performance for that. What we've seen over the last 4 years is a change in terms of how we release Java. And this was something that Oracle announced with JDK 9. In the past, we've had anything like 2, 3, even 4 years between releases. What we now have is one release every 6 months. In February and in September, we have a new version of Java. And that's proved to be really powerful in terms of delivering small new features to the language and also big features as well. But lots of new things have come through very, very quickly. And we've seen the pace of change much faster now in Java than we've ever seen before. But there's another thing that this has also made possible by having this faster release cycle is the idea of incubator modules and preview features. Now, incubator modules are all about adding APIs, class libraries to the platform, and preview features are about things that you can change in terms of the language. And then there's also tools and other things as well. But the key thing here is that when new features are added to Java, we don't add them and make them a fixed part of the standard straight away anymore. All the language changes that I'm going to talk about over the next couple of hours are introduced as preview features now. And what this means is that we have the ability to take feedback from developers and see if those features work the way that they really want them to. If there are situations where it doesn't quite do what developers really want it to, they can provide feedback, and then the developers of the platform have the chance to make some changes before it becomes a final feature. And we'll see as we go through that actually is working very, very well. There's been a couple of cases where this has enabled us to address concerns that we have from developers. The problem, though, or drawback, if you like, is that by having a release every 6 months, most users, especially if you're in an enterprise, if you're in a big commercial system, you don't want to update your Java version every 6 months. That's just too fast. The amount of testing that's needed, the amount of verification and deployment and so on is just too much. And so people are looking for a solution where they can have Java changing at a faster pace, but they still have the ability to use older versions for longer when they want to deploy particular applications. And the answer to that is what we call long-term support releases. These are really targeted at enterprise users. What it says is that certain releases will have updates, security patches, bug fixes, and so on provided for them for an extended period of time. Other releases, we just get 6 months, but the long-term support releases will have these continued updates. And when Oracle made the change to announce this was when JDK 9 came out. And they said that JDK 8, which was the one that most people were using at that time, that would be the first long-term support release. They would continue to provide updates to that. Then JDK 11 would be the next one. And then after that, the idea was to have a long-term support release every 3 years, meaning every 6th JDK. And we've seen just recently with September, JDK 17 was released, and that's the current long-term support release. Now, Oracle then made a bit of a decision to propose that we would move to 2 years between long-term support releases. And so JDK 21 will be the next one. And this is one of those changes which I was doing some presentations this week in Sweden, and I did poll the audience when I was talking about this and asked them whether they thought 2 years was a good length or 3 years. And it seems that people are quite divided on this. So it'll be interesting to see how people feel about having 2 years between long-term support releases rather than 3. I know there's also been some discussion about libraries and how to update those and keep them consistent. What's also changed as well with Java is that we now have a much bigger choice of distributions of OpenJDK. OpenJDK is the open source version of Java, and people can take that source code, they can build it, and they can provide that as a distribution to users. This is very much the same as we see with Linux open source project plus the libraries. People like Ubuntu, people like Red Hat, Debian will take that code, they will generate a distribution that you can install on your machine, and then you can use it to run your applications. In the past, most people have pretty much used either the Sun or the Oracle JDK, but now with some licensing changes that Oracle made, people have said, right, we need more choice, and so we've seen a bigger selection of distributions. And in fact, let's talk a little bit more about that. As I say, OpenJDK is open source. It's an open source project for the development of the Java platform. And I think this has been really successful. We've seen over the years, it's now 15 years since Java was open source. We've seen a lot of contributions. Clearly, Oracle, as the owner of the Java trademark, owner of OpenJDK trademark, they're the biggest contributor in terms of new features and ideas. And they really sort of make the big decisions about what's going to go into Java. But there's lots of other people involved as well. So you have Amazon, who have engineers that work on OpenJDK. You have Red Hat, you have SAP, you have Azul that I work for. And we all contribute lots of different things to OpenJDK, whether it's bug fixes, security patches, new features, and so on. And then, as I say, people will take that code, they will then build that, maybe make some changes, and provide different distributions. As you can see, you've got Oracle JDK still, you've got Corretto from Amazon, you've got Temurin, which is part of Adoptium. This used to be Adopt OpenJDK, it's now under the Eclipse Foundation. Azul have Zulu as their build, and there are other ones as well. Okay, so let's start talking about what's changed in terms of Java. And as I said, I want to talk a little bit about JDK 10 first, because that has this idea of local variable type inference. The first thing we need to talk about then is the fact that in Java as a language, we need to be able to store information. I mean, it's basic idea behind programming languages. And the way we do that in Java, because it's object oriented, happens in a couple of different ways. So the first thing is that if we define a class which encapsulates state and behavior, part of that will be a number of instance fields. And the instance fields will store data relative to that object, and they will exist for the lifetime of that object. They're part of the object. The important thing about that is that the initialization of those fields is guaranteed by the compiler, meaning that if you create an int as a primitive variable, even if you don't set a value for it, the compiler will set it to be 0. Same with a Boolean, it will set it to false. And if you create a reference to an object, if you don't set a value for that, the compiler will set it to null. So you're guaranteed that the compiler will set values for these things. Now, the other thing that you can have in your code is if you look at a method, within a method, you can have local variables. These are the ones that you use in order to perform whatever code your method is doing. And these variables are scoped based on different sections of code. Scoping is where the objects or where the references are valid, and it could be across the whole method, it could be within a for loop, it could be within a while loop, or even a block of code. So there's different ways that you can scope variables within Java. The important thing about these is that the initialization is not guaranteed. If you don't set a value for a particular variable in your method, then you'll actually get a compiler error. The compiler will say, nope, you haven't assigned a value, so you need to do something with that. One of the things that's really good about local variables is they are cheap, because most of the time they're allocated on the stack, meaning you don't have to find space for them in the heap, you don't have to then garbage collect them, you just put them on the stack, use them. When the method gets finished, everything gets popped off the stack and the variable just disappears. And if you look at the way that we use local variables, it's often the case that the name of the variable is actually more important than what type it is, because you're using it in a sort of confined area. So local variable type inference. The first question we need to ask ourselves is, why would we add this to Java? And I came up with a couple of reasons for this. And the first of those is a little bit facetious, shall we say, which is that JavaScript has it, so it must be good. I don't think that's actually necessarily a good answer, but I mean, it is one approach. But if you look at the way that we use Java, especially from JDK 8 onwards, with the introduction of streams. Now, streams will hide a lot of the intermediate types that are being used. In this simple example, what I'm trying to do is create a list so that I can see that the type of the object I'm going to get is a list, and I'm passing in a list which has some names in it. So there's strings. If I create a stream of that, then I get a stream of strings. Then I pass that into filter, I still get a stream of strings. I pass that into map to get the record out of the whatever string it is, and I get a stream of records. And then I can collect that into a list and I get an array list of record. The important thing is that we can see exactly what's going on in this code, but we don't need to understand what the types are specifically. We just know that we're going to get a list back, passing in names, but we don't really care about what's happening intermediately. It's just the process that we're interested in, not necessarily the types. So why not take this idea and expand it elsewhere in the Java language? And that's really what local variable type inference is about. So one of the things is that we can make code more concise, but very importantly, and we'll come back to this later on, is not losing readability. If you look at the way that we want to change Java over the last couple of years, the changes that have been made, much of it is about eliminating boilerplate code from our applications, but not losing the ability to see quite easily what's going on in the code. The last thing we want to do is end up with a programming language that looks more like Perl. I don't know if anybody's ever done any Perl programming. I know I have, and it's very difficult to read what's been written, even when it's you that's written the code. Okay, let's look at some simple uses of local variables as we do in Java. Well, obvious one here is that we have an array list of type string called nameList, and we want to instantiate an object of that type. If you look at this code, you can clearly see that we have to define nameList as a specific type. So we say it's an array list of type string. We instantiate a new array list of type string. So it's rather redundant to have array list of type string on both the left-hand side and the right-hand side of the evaluation. We're just, adding code for the sake of code. Now, In JDK 7, we did sort of tweak that a little bit, and we did introduce the idea of type inference for generic parameters. In this case now we can say list of type string, user list, and then we say new array list, but we don't have to specify the type of the generic parameter because we know the compiler can determine from the left-hand side that because we're creating a list of type string, then the array list must be an array list of type string. So it can infer the type for us, and we don't have to specify it explicitly. So that's good. I mean, it makes a slight change, but we still need to go further with this. Similarly, if we create a stream from our user list, then we have to specify the type stream of string. Now we can use local variables in a loop. So we could say for string name over user list, and we can also use it within a more traditional for loop and say for int I equals 0, I less than 10, I plus plus. Okay, all good. Let's look at this now if we use local variable type inference. So the first one, now we don't have to specify a type on the left-hand side. We use var as a keyword and say user list is a variable. So we know that it's a variable, and we're going to assign it to a new instance of array list of type string. The compiler can very easily infer that the type of user list is an array list of type string because that's the object we've just created. Nothing clever here at all. The compiler can work it out for us. Similarly, if we create a stream from the user list, and we say that the stream on the variable that we're going to create called stream is a var, then the compiler can infer, because we know user list is a list of strings, then we're going to get a stream of strings. Nothing complicated for the compiler to work with there. If we wanted to, we could use var in our for loop. We could do for var name over user list. Once again, we know that user list contains strings, so when we iterate over it, the name that we're using there to reference the strings in the list will be a string. And then finally, if we wanted to, we could say for var I equals 0, I less than 10, I plus plus, and that will infer int. This is the first example I'm going to show you where I would absolutely say to you, don't use var in this case. The reason I say don't use var in this case is because var has 3 letters. Int has 3 letters. You're not saving anything in terms of the code that you're generating. You're just obscuring a little bit what the type of I is going to be. So if you didn't know straight away that it's going to be an int, you'd think, well, is it an int? Is it a short? Is it a byte? So just leave it as int. One of the things you can do with var is to tidy up code and make it more readable. Now, here's an example where I've created a simple try with resources. And I wanted a buffered reader, and I've kind of deliberately made this quite verbose. I've said we need to create a buffered reader from an input stream reader for which we need an input stream. And in my code, obviously, I've got input stream equals get socket.get input stream reader equals new input stream reader with the input stream, buffered reader. I go on, and it just is very messy as code. Sure, I can read through that eventually and figure out what's going on, but if I wanted to look at it quickly and see what's happening, that's very dense in terms of the code. If we use var, we can just tidy that up a bit and say, okay, we've got input stream reader, buffered reader. Just makes life a little bit easier for us. So this is a good use of var in this particular case to make our code more readable. And as I said, we don't lose any of the information. We can see from the right-hand side that we're creating an input stream. And also very importantly, because I've named the variables accurately and descriptively, then we know that we've got an input stream reader, and a buffered reader. The type is very obvious from the name of the variable. Now, one of the things that we have to understand about local variable type inference is that even though it allows the compiler to infer the type for us, what it doesn't do is change the fundamentals of the Java programming language. By that, I mean that unlike JavaScript, in Java, when we use var, the type is very much static. Once you have assigned a type to a variable, you cannot change it in your code. In this example here, I've got var name equals Simon. clearly I've assigned a string literal, so name must be a string. That will be inferred by the compiler. I can change that value so long as I change it to another string. I can say name equals Dylan, it's still a string, it's still the same type, there is no problem with that. However, if I were to try and change name to be 42, 42 is not a string, and even using boxing, I can't convert it to a string. So the compiler will say, no, hang on, it's an incompatible type, int can't be converted to string. So it knows that name must be a string, and there's no chance, as you would do in dynamically typed languages like JavaScript, where it will suddenly just say, okay, we'll store 42 in name, and name will now become an int reference rather than a string reference. So this doesn't change any of the static typing that we have in Java. Even though we've got local variable type inference, it doesn't change static typing. Final and non-final. Now, this is one of those things where, again, if you look at other programming languages, they may do things slightly differently. var simply indicates that the compiler is going to infer the type of the variable. It makes no distinction about whether that variable is mutable or whether it's final. If I say var name equals Simon, I haven't specified that it's final. So I can change the value of name and the compiler will be quite happily with that. If I do want it to be final, if I want it to be immutable, then I need to add the final modifier and say final var name equals Simon. Some languages do have a shortcut which combines the final and the var. For example, val in some languages. So you could say val name equals Simon, and that's equivalent to making it final. The decision was made by the developers not to have that kind of functionality. It was just done that way because they decided they liked it as having var not being final and then having to explicitly add the final modifier to it. A lot of people argue that you don't often make local variables final because, well, they're variables, aren't they? So you want to be able to change their value as you manipulate the data. Action at a distance. This is one of those examples again where we might want to not use local variable type inference. If I have bad naming of my variables, I would say, okay, var L equals new array list of string. Great. So I've created a new array list and I know that L is going to be an array list of type string. Similarly, if I do var S equals L.stream, then in that case, it's fairly obvious what's going to happen. I can see from the line above that I've got an array list of type string, so my stream will be a stream of strings. In that case, I don't lose any readability. I can still see exactly what's going on. However, if I have lots of complex code and I want to use L much lower down, and I suddenly say var n equals L.get0, because I haven't named the array list particularly well, just used L, there's nothing to indicate to me or another developer what the type of L is. And because I don't have to explicitly state the type on the left-hand side of N, then I'm not getting any information from that either. So we would struggle if we can't see where L is defined. We'd struggle to immediately go, N is what? It's an object that has been retrieved from this list, but I don't know what kind of list it is. You then have to scroll all the way back to find where L was defined, or if you're using your IDE and it has the ability, you can hover over L and it will tell you what type it is. But that's not what we want to do. So this is an example where I wouldn't recommend doing coding this way. Use more explicit variable names. Don't use short variable names in this particular case. If you only had the 2 lines at the top, you can get away with it. But as soon as you have code and then you try and use things lower down, you lose the readability. Some of the edge cases of local variable type inference. Not everything can be inferred. Right, what do I mean by this? Well, if I create an array of ints, the first 6 prime numbers, 2, 3, 5, 7, 11, 13. Okay, I can do that very easily. I can define an array of ints, and then by using the braces, I can specify the values I want to put into that array. You might think to yourself, well, okay, let's avoid using the int array definition, and let's just use var and say that the first 6 primes and Let's see what happens. Well, that won't compile. What you get is an error message that says cannot infer type for local variable first 6 primes. Array initializer needs an explicit target type. The reason this won't compile is that if you look at the definition that we have of the values we want to store into our int array, so the braces and 2, 3, 5, 7, 11, 13, that is what's called in Java a polytype. Polytype is one that can represent more than one type. So because it can represent more than one type, the compiler is faced with a choice. And the compiler says, well, if I can't determine exactly what the type is in the var, then I won't compile it. I won't take a guess. I won't take the first one. I'll ignore that and I'll say, no, I can't determine it as a explicit type. Because, well, one of the things we could do here is we could say, okay, var first 6 primes, and then we can specify and force it to use a particular type. So we're saying new int array, and then our values, because now the compiler can say, oh yes, you are dealing with an int array, so I can say what first 6 primes type is explicitly. And one of the reasons we can't actually make a definition is because if I did this and I said var first 2 primes equals new integer, the wrapper class as an array, that would also be quite valid. And in fact, I could have done first 6 primes in the same way. But you can see now that because we could define either an array of ints, primitive types, or an array of integer wrapper objects, then the compiler wouldn't know when we say var first 6 primes equals the contents of those brackets, whether to use an array of ints or an array of integers. If it can't determine which type to use, then it will give you the error. Types are required on both sides. Let's say we want to do this, var list equals null. Well, you could say, okay, hopefully that will compile, but actually the error you're going to get is cannot infer type for local variable list, variable initializer is null. Now, null in Java is a bit of a special value because if you think about the type hierarchy in Java, you've got object at the top. Object is the superclass of all objects, and then you inherit from that through other subclasses. Null actually represents every single type in Java. So it can be used for any type in Java. If I say var list equals null, once again, the compiler doesn't know which type should it use because it could be any type. There is an argument that would say, well, if I replaced var with object, and because that's the superclass of all classes, then I could say object list equals null, and that would compile quite happily. So var could simply infer object because it's the highest type that we can use, and that would compile. But again, decision was made in terms of the way that this works to say, no, we won't do that. We will say that in this case, the null, because it represents any type, it is ambiguous, so we will reject that. Similarly, you can't do this. You can't say var list on its own, and then even on the next line, say list equals new array list of type string. That will give you an error, and it will say cannot use var on variable without initializer. You must initialize the variable straight away so that the compiler can infer the type for you. Again, there is an argument that would say, well, so long as you have an assignment to list somewhere in your method, then what's the problem? The compiler is going to look at the whole method. It will be able to figure out that you have made an assignment for list, and therefore it can infer the type of list. But again, this is about readability. It's about understanding the code. If you say var list, you have no idea at that point what list type is going to be. And if the assignment is much further down the code, you have to search to find out where that assignment is made so you can figure out what the type of list is. Remember, var is about helping with readability of code. We want to make code just as readable as without using it. And in this case, if we were to allow this, it would potentially affect how we can understand the code. Literals with var. You have to be a little bit careful here because sometimes they don't do the things that you expect them to do. Here's an example that is good. If I take these 4 assignments, I've got boolean ready equals true, I've got char ch equals x, I've got long sum equals 0 long, and I'm explicitly stating it's a 0 long, and then I've got string label equals foo. Fine. I could change all of those to use var, and there is no ambiguity here. The compiler can look at that and say, I know exactly what type to use. Ready will be boolean, ch will be our char, sum, because I've made it 0 and then added the L modifier, it knows it's going to be a long, and label is going to be a string. Be careful though, because with literals, when you're using numbers, this can be dangerous. Here I've got an example where I've got 3 numeric values. I've got byte flags equals 0, I've got short mask equals 0x7fff, and I've got long base equals 10, but I haven't used the modifier to force it to be a long. Okay, if I change all of those to be var, you might think, okay, well, how does the compiler deal with this? Well, the compiler doesn't look at those values and say, what's the smallest value, or what's the smallest primitive that I can fit those things into? 0 clearly will fit into a byte, or a short, or a long. 0xFFF will fit into a short, yes, but it will also fit into an int. And base being 10 would fit into a short or a byte. So the compiler in this case will say, we'll use one of 2 types. All of those can fit into an int. So if the value will fit into an int, it will infer an int. If it's beyond the capability of storing an int, then it will be a long. But that's the only 2 things that it's going to use in terms of inferring the type of a numeric literal. It's either int or long. So the problem we get here is that we have specified byte, short, and long, and those have specific sizes associated with them. So we've got 1 byte, 2 byte, and 8 bytes. If we're sending that information across a network connection, for example, and we expect the data to be encoded in that way, so we read the first byte, then we read the next 2 bytes, then we read the following 8 bytes, expecting that to be the way things work. If we switch to using var, now suddenly we've got 4 bytes, 4 bytes, and 4 bytes. When we try and read 1 byte followed by 2 bytes followed by 8 bytes at the end, we're going to get completely different values to what we expect to get, and they'll be wrong for our code. So this is where we need to be careful when using literals with var. Beware of multiple type inference. I mentioned at the beginning of this section the idea that in JDK 7 we introduced the diamond operator. Diamond operator said that we could have the compiler infer the type of a generic parameter. Simple example here, I've got a priority queue of integer on the left-hand side called item queue, and when I instantiate that, I simply use new priority queue diamond operator. The compiler will infer the type for us. So when we use var, we need to be very careful, because what's going to happen here is the compiler is going to go, right, I need to know what type item queue is. So it looks at the right-hand side and says it's a new priority queue, fine, but what's the generic type parameter? Well, we're going to get primary type inference here. And this is one of those situations where you think, the developers might have wanted to do this differently. What happens here is that the inference that the compiler will use, it will say, well, I don't know what the type on the left-hand side is, so to infer something valid there, I can only use object. And so we get primary type inference saying that the priority queue is of type object, and then var will look at the right-hand side and say, oh, we've got a new priority queue of type object, therefore the type of item queue is priority queue of type object. If we then want to use that, because now we're inferring the priority queue of object, then we get an error if we try and store something which is a priority or using an integer into that. Program to an interface. This is something we do a lot in Java. We use interfaces rather than concrete types. It's object-oriented language, so we use polymorphism to view objects as different types, so long as they are of that type. We often do this. We say list of type string, mylist equals new array list. And that's fine because we just want to deal with a list. We don't care whether it's specifically an array list or some other type of list. We just need to know that we're dealing with a list. The thing is, when you use var, var will always infer the concrete type, meaning that mylist, the type of it, will be an array list of type string. Because so long as we remember to put the string generic parameter rather than using the diamond operator, we'll get an array list of type string. This does not break any code. So even though we're not having a list specifically, we're not using the interface, because an array list of type string is a list of type string, anywhere that we want to use mylist, if we're passing it to another method which does take a list of type string as a parameter, that will work. There is no difficulty at all with using the idea of a var where you get the concrete type rather than an abstract interface or an interface. So it will work in exactly the same way. The only thing that might be different is if you were to try and call methods on mylist which were part of array list, which you can do if you use var, but you couldn't do with using list of type string. But as I say, to all intents and purposes, the way this will work is exactly the same as you had before. So you don't need to worry about the fact that you're programming through an interface. It will still work. Lambdas and var. And this comes back to the example that we saw earlier on of polytypes. If I define a predicate of type string called blank line, and I'll say that the lambda expression I want for that is s is the parameter and the body of the method is s.isBlank. So it returns a Boolean. Essentially, I've got an implementation of a single abstract method in the functional interface called predicate of type string, and I've provided that implementation. I could then change that to use var, but if I do that, it's not going to compile. It's going to not compile for the same reason that we saw earlier with the array of ints. It will say lambda expression needs an explicit target type. Reason for that is that, yes, predicate of type string will certainly match that lambda expression. But because all we need is a functional interface that has a single abstract method that takes a string as a parameter or a type as a parameter and returns a Boolean, then I could create my own lambda expression. I could create my own functional interface that will implement that in the same way. So the compiler has many different choices potentially for that. And so there's ambiguity. The compiler will then say, no, you're right. It's not a single thing that we can define, and therefore it won't actually compile it. Intersection types. This is a really kind of interesting use of var, where we can do some clever stuff that we couldn't do before. In Java, we have the idea of generic types. And these were introduced way back in JDK 5. And we can define something like this. We can say, I've got a method called getData, and it's going to return something of type T. So it's generic. And when we define T, we say that T is something that, and this is where the definition of generics, I think, is a little bit wrong. So we say T extends closable and iterable of E. Closable and iterable of type E are both interfaces. They're not classes. So I think that they should have used implements rather than extends, but they chose to use extends for both classes and interfaces. So we're stuck with it. But essentially what they're saying is that the type that we get back from getData is some class which implements two interfaces, closable and iterable of type E. Fine, okay. So this is, the important thing here is it's valid Java syntax to say that T extends multiple interfaces, closable and iterable of type E. The problem we face is if we create a method called first match, and that's going to take a predicate condition, and then we want to do something with the data that we get back from the method that we just described. So we've got get data, and that's going to return some elements. If we want to use those elements as both the types that both the interfaces that are returned, we're a little bit stuck in terms of how we define the type of elements. What we need is something which implements closable. Okay, that's fine because we know that the thing that is returned by get data implements closable, and if we want to use the try with resources construct, then we know that elements has to implement closable. So that's all fine. And we also know that if we want to use elements with .splitterator, then we've got to have elements implement iterable of type E. What we're then stuck with, as I say, is the problem of what do we use in terms of the value of XXX. We can't define a type that says closable and iterable of E, because in the case of a local variable, we can't use that ampersand to say it's both of those interfaces. What we typically do is one of two things. We either create a new class, which is our class which implements both closable and iterable type E, so that we can then have elements be of that class, or we create an interface which does the same thing. So an interface extends both closable and iterable of type E, or implements both closable and iterable of type E. So we have a type that we can use for elements. The problem with doing either of those things is we're introducing another type to our application. And if this is the only place where we use it, we're getting type pollution. We're just adding a type for one particular place. What we can do now, though, is we can use var, because var will allow the compiler to infer a type. And this is one of those really kind of nice things, because we have the idea of non-denotable types in Java. Java is a language, we can define a set of types, but the JVM can actually understand more types than you can express in the Java language, which is good in this case, because the compiler can then say, right, I need something that will implement both closable and iterable of type E, and I can just do that underneath the covers, and I can generate something which will have both of those types associated with it, and then the compiler will generate code that works with this, and I don't need to create a separate class or a separate interface that I then use for elements. So if it's only used once, this is great. I could just use var and everything will work. So the compiler will infer a type that's impossible to express in the Java syntax. Inner classes as well. So this is, again, a slightly weird bit of code, but it shows what you can do. If we create an inner class in this case, so we say object fruit equals new object, and then we actually add some things to the definition of object. So we have a string, an instance field called name, which is apple, and then we have a method in French, which returns a string and returns pom. That will compile. That will compile quite happily. There's no issue with that code, which kind of I find a little bit strange because object doesn't have those things in it, but it will compile. However, if you try and use those things, if you do fruit equals plus fruit.name and you call name on fruit, because it's an object doesn't have a name field. Similarly, object doesn't have an in French method, then the compiler will reject that and say, no, you can't do it. However, if we say var fruit equals new object and then add those things to it, then the compiler will again generate one of these non-denotable types, meaning a type that can't be expressed in Java but can be understood by the Java virtual machine. So now we've got this sort of magical type that we generate by the compiler, and when we call fruit.name or fruit.inFrench, it will work, and the compiler is quite happy with that. So it's kind of a couple of edge cases where local variable type inference gets kind of interesting. Last thing to say about var is that it is a reserved type, not a reserved keyword. Now, Java has a number of keywords, which are things that you can't then use for variable names. For example, if you wanted to use int, you can't use int as a a variable name because it's a reserved word. Same as while. You can't use while as a variable name. Obviously, it would have been bad if we had added var as a new reserved word in Java and you couldn't use var as a variable name, because I'm sure that lots of people have used var in code and then it wouldn't compile anymore. So what we can't do in JDK 10 that we could have done but never would have done in JDK 9 is create a class called var with a lowercase v. That's because, as I say, var is now a reserved type. Now, in Java, we always use uppercase, well, the tradition is to use uppercase letters for the beginning of the name of a class. But in this case, we're now saying we can't use the lowercase v with var, and that won't work. What we can do is we can still create a class with var as an uppercase name. So that's fine, that works, we don't break anything with that. Essentially then, what it allows us to do is this. We can do var equals new var. I don't recommend that, but it is compilable. I did it, I checked it, it does work. And so you can use var as a variable name, and you can use var to indicate that the compiler is going to infer the type of var. Okay, so that was JDK 10. Let's talk a little bit about JDK 11 and what happened there. There wasn't much in terms of significant changes. They did make one small change to local variable syntax, and that was to do with Lambda parameters. So if we look at a simple example here where I'm taking a stream, I'm mapping it, and I'm using a Lambda expression to indicate how I want to map that stream of strings. I want to map them to the lowercase version of those strings. Fine. So I have my Lambda expression which says it takes s as a parameter and then calls to lowercase on whatever s is. In this case, when they defined Lambda expressions and the use in streams, they said that this was going to use type inference. We do not need to explicitly state that s is a string. The compiler can infer it for us because it knows that it's getting a stream of strings from that list. Okay. What we can now do in JDK 11 is this. We can add var. So we can say map, and then we say var s maps to s.lowercase. So you look at that and you go, why would I do that? What possible reason would I have for adding var to indicate I want type inference of the type of s, given that I already use type inference when I use the Lambda expression above, because the compiler already infers s, so why use var? There is only one situation where you would use that, and the situation is if you want to use an annotation, because if you want to use an annotation, you must have a type between the annotation and the local variable. That is just the way the syntax works. You could state the type explicitly and say string s, but if you don't know, if you've got a complicated stream going on, then it's just easier to say, look, let the compiler deal with it. So I'll say I want to use an annotation, not null, and then rather than me trying to figure out what the type is, let the compiler do it for me and just use var so that it will say use type inference for that and everything works. So like I say, small change, and I don't expect many people will use that too often. A couple of other things that got added in JDK 11, talking about APIs this time. So they added some new methods to the I/O side of things, and specifically around input stream, output stream, reader, and writer, the idea of null input streams, output streams, readers, and writers. And essentially what that does is give you an input stream that you can read exactly 0 characters from, and give you an output stream or a writer that you can write as much data to as you like, and nothing will be done with it. Think of this as being the same as in Linux, where you have /dev/null. So it's the idea of, you can just throw data into it or read nothing from it. And there are certain situations where if you're using streams particularly, these might be useful because you need a null input or a null output stream. Also in optional, the class, they added a new method there called isEmpty, which is the opposite of isPresent. So you can then test to see if there is a null in your optional versus is there something in your optional. The string class actually got a few new methods in JDK 11. First of those is blank, I think you can probably guess what that does. It tests to see whether you've got a blank line, a blank string. Also, you can, if you have multiple lines in your string, then you can use lines to get a stream of strings, which are the individual lines in that bigger string. Repeat will repeat a string a certain number of times as specified by the parameter. And then you've got strip, strip leading, and strip trailing, which will remove white space from your string. In the case of strip leading, from the leading white space, trailing white space, and strip will remove it both leading and trailing white space. The observant amongst you will say, well, hang on, what does strip do that trim doesn't do? Because we already have trim that will remove white space from both ends of a string, so why do we need strip as well? And the answer is that all these three methods, strip, strip leading, and strip trailing, use a different definition of white space to the way trim does. Trim uses a very simple white space definition, which is basically space and tab and new line. In these three methods, we use the Unicode definition of white space, which includes a whole host of characters that you probably never really realized existed. So like vertical tabs, for example, are considered white space. So should you put one of those in there, it will get stripped out. And then in JDK 11, probably my favorite feature was the introduction of a new static method on predicate. And the method is called not, which takes a predicate. Again, if I look at an example here, I'm taking a stream and then I want to filter it. And the way I want to filter it is to remove blank lines from the stream. And I can do that by saying, I want only the lines to go through which are not blank. And I can do that by using a Lambda expression where I say S is the input string, and then the body of the predicate is to say not S dot is blank. Okay. If I use predicate not, I can change that. I can say filter predicate dot not, and then I can use the method reference on the isBlank method and say string is blank. If I then do a static import on predicate not, I can change that, make it a little bit simpler, and go filter not string is blank. So it just makes it a little bit more readable in my mind. So I like that as a simple feature. JDK 12. So JDK 11 was the last long-term support release. Now what we're into is features that have been added since that. So now we're looking at what's going to go into cumulatively into JDK 17. If we look at Java, the language, Java, right from the very beginning, has had the idea of a switch statement. It's a sort of multiple if-then-else kind of construct. And what this does is allow us to do that, but it is a statement. A statement is where you perform a set of actions, but you don't generate a result. So you can't assign what a switch statement does to a variable because it's a statement. And if we look at the way that that works, switch statement came from the C programming language. When Java was created, the developers, people like James Gosling, they were very familiar with C as a programming language, and they said, let's take the basic syntax so people know how to use loops, they know how to use switches, and so on. All good. But the thing with the way that switch works in C, and therefore works in Java, is there are a couple of situations where the syntax can be a bit clunky and doesn't necessarily work in the way that we want it to. First of those things is that for every block of case statements we have, we must remember that in the body of that, where we do our actions, then we have to have a break statement. If we don't have a break statement, we're going to drop through into the next set of case statements and do whatever that does. That's the way it's designed to work. It's not an error. I know I have forgotten at some point to put a break statement in a set of cases, and I've found it difficult to solve a bug that gets introduced by that. When I ask people about this in real audiences, I know that pretty much everybody puts their hand up to say that they've done that as well. So there's things like that which make life a little bit difficult. Similarly, the scope of local variables is not quite as intuitive as we might want it to be. If we look at an example of how the switch statement is used in a very common pattern, what we're doing here is we're taking one variable, day, and we're going to switch on that. And then we want to assign a value to another variable, number of letters. And we can see here that we've got switch on day, and then we've got case Monday, case Friday, case Sunday, assigned to number of letters, 6, because there's 6 letters in it. Then we've got to remember to put our break in there. And similarly for Tuesday and Thursday and Saturday and so on. As I said, one of the drawbacks here is that if we forget to put a break in, let's say Tuesday, then we're going to drop through to Thursday and Saturday, and the value assigned to number of letters will now be 8 rather than 7, which is not what we want. But also, if we didn't use a local variable for number of letters, if we use an instance field, which, remember, gets automatically assigned a value, if we forgot to put an assignment for number of letters in one of those case blocks, then we'd end up with a value of 0 rather than whatever value we wanted for that. And again, it makes it more error prone, makes it harder to find bugs and figure out what's going on in our code. In JDK 12, we now have the idea of a switch expression. First thing to understand there is because it's an expression, it executes a set of actions, but also generates a result that can be returned and assigned to another variable. This is really good because immediately that solves one of our problems. We take whatever switch returns and we assign it to number of letters. We do that once and we do it once only. And therefore we eliminate that potential problem of forgetting to assign a value to number of letters. We can see here that the code is a lot shorter than the code we had on the previous slide. But importantly, we're not losing any of the readability. Again, this comes back to what we kind of said earlier about how readability is is very important in Java and making sure you can understand what's happening. So we do our switch on day and we assign whatever that returns to number of letters. And then in the body of the switch, we've got our case statements. One of the things here that I find is just amazing is that now we have this idea of shortening our code because the developers have discovered this incredibly powerful feature called a comma separated list. Rather than having case Monday, then on a separate line case Friday, and on a separate line case Sunday, we have case Monday, comma Friday, comma Sunday, all on one line. Wonderful. Then we borrowed some of the syntax from the Lambda expression. We use the arrow operator. Right-hand side of the arrow operator is the value that will be returned from the switch expression. Good thing is the compiler can make sure that we always assign, we either return a value from there or we throw an exception. So that way we won't have a situation where we forget to return a value. As I say, much shorter code, much better, less error prone, and also not losing any of our readability. We can, if we want to, combine the old style syntax with the new style switch expression. Again, we can take switch on day, we can assign the value of the return to number of letters, but this time we'll separate out our cases onto individual lines. But this time, rather than using the arrow operator, the developers decided to overload the break keyword. And you can use break in a couple of different ways in Java. You can either break from a switch statement, or you can break from within a loop to a variable. To a label. What they decided with the way of using this switch expression was to say that they would also use break followed by a number, and that would be the value returned by the switch expression. So case Monday, Friday, Sunday, break 6, Tuesday, break 7, and so on. That's we'll come back and we'll talk about that in a moment as to whether that's a good idea or not. Another thing that got introduced in JDK 12 from an API point of view was that we added a new collector to the streams API. And this is called teeing. Teeing takes 3 parameters, 2 collectors and by function. And as you can see from the diagram here, what happens is that we take the input stream and we duplicate it so that we end up with 2 streams which are identical. Those 2 streams get passed through the collectors that we have defined as parameters. The results of those collectors then become the inputs to the by function. So by function takes 2 arguments, and then we apply whatever the function does and generate a result. To give you an example of how that actually works, what we can see here is we've got a stream of numbers that I've created, 145217. I pass that into collect, and I statically import teeing. So I use teeing with 3 parameters. First of those parameters is that I want to take all the values on the input stream and add them up. So I sum into a double the values on the input stream, total of those values. The second collector I use counts the number of elements on the input stream. So I've got 2 values now, the total and the number of elements in the input stream. I pass those as parameters into my teeing collector, into the by function, and I can then say divide the sum by the number of elements, and that will give me the average. Now, obviously, I could have done that with a single method call, but it shows you how this could be used if you wanted to do something more sophisticated and manipulate data in different ways. JDK 13. What did we get there? Well, the first of these things was what's called text blocks. Text blocks allows us to define string literals in a slightly different way. Again, right from the very beginning, Java has had the idea of strings of characters in the language, and it's a sort of a fundamental type string. And if we want to define a string, we use double quote to indicate the start of the string, double quote to indicate the end of the string. This is all good, except that things like multi-line strings and like unusual characters are harder to put into those strings. If you want to do a multi-line string, you've got to concatenate things, you've got to put \n in there and various things like that. What text blocks allows us to do is to change the way we define a string literal. Rather than using a single double quote, we now use 3 double quotes to indicate the start and the end of a text block. We borrowed the syntax here from Python, just a simple way of doing it. And everything that follows our 3 double quotes is considered part of the string up to the closing 3 double quotes, almost. And I'll explain why I say almost in a moment. So here, what we've got are some HTML tags, and those HTML tags have indentation associated with them. If we print out the result of this string, what we will see are our HTML tags, and they're indented. But they're also left justified, so there is no space before the opening and closing HTML tag. If we look at the text block above, we see that there's a lot of white space on the left. And you kind of think to yourself, well, hang on, how do I know how much gets stripped out? Because it isn't clearly stripping out all leading white space because I've still got the indentation on my tags. And the reason for this is that the developers added the idea of incidental white space. If we didn't have this, we would have to push our tags over to the left-hand margin, and that wouldn't necessarily look good in terms of the layout of our source code. If we've got indentation for our source code that we like to have, then by forcing those things over to the left-hand side to avoid additional white space would really kind of mess up the way that our source code looked. What happens here is that the white space up to the first character in our text block is considered incidental white space and gets stripped out. We don't strip out all the white space, only the incidental white space. That way we still get the indentation that we expect for the tags. Second thing to be aware of is that the 3 double quotes must be followed by a new line. You can't start your string immediately after them. You have to have a new line, and then everything from there is considered part of the text block. And then the last thing to be aware of is that if you look at the closing HTML tag here, I've got 4 spaces after that tag, and those will be stripped out. Now, if you read the JEP that describes how text blocks work, the reasoning for this is that if you had a line that only had white space on it, they actually want to be able to strip out all the white space and sort of compress down the way things work. So, but it's a little bit difficult, you see, because you look at that and you go, well, what if I do want white space after my HTML tag? How do I get that? We'll come back to that in a moment. Now, if we want to have our HTML tags moved over to the right, and so we do actually want some padding in the way that those are laid out, we can do that. What we do is we take our closing 3 double quotes and we drop them down to the next line, and then we move those over by a certain number of spaces to the left. And that way, when we print out the results, what we'll find is that by moving the 3 double quotes over 4 spaces, now we have 4 spaces of padding plus the indentation that we expect for our HTML tags. There's only one tiny little drawback with that, which is that by dropping the 3 double quotes down onto the next line, we also get, well, we get intentional indentation here, plus some incidental white space, but then we also get an additional blank line. So you can see that because we've dropped those 3 double quotes down, now we've got that extra blank line that we weren't expecting. So the combination here of incidental white space, which is white space we don't want in the text block, plus the intentional indentation, which is white space we do want in our text block. Switch expressions. Hang on, I've already talked about switch expressions, so why am I going to talk about them again? This is a perfect example of how preview features work and the benefits that they can give us. As I said, if we want to use a switch expression, we can combine the old style switch statement syntax with the new switch expression. I said you could have case Monday, case Friday, case Sunday, and we used break followed by a value to indicate what was going to be returned from the expression. Developers looked at that and they said, yeah, we don't like the fact that you've overloaded break in that way. Sure, if you have a label, the compiler can differentiate between breaking to a label, because a label can't be a number, and in fact a label can't even start with a number. And so when we break with a number, the compiler will know that that's what's going to be returned from the switch expression, versus breaking to foo is where we're going to break to a label. But we don't like that, so we think it should be done slightly differently. And the developers looked at the feedback and they said, you know what, you're right, let's change that. And they said, rather than using break as the way of indicating the value to return from the switch expression, we'll use yield instead. So now we've got a different way of doing it. Feedback from developers has changed the way, and it means that developers are getting more what they want in terms of the way that the development language works. Moving on to JDK-14. And JDK-14, I think, was really one of the best releases recently because it had a couple of very useful features in it. Let's talk about simple Java data classes first. And we do this a lot in Java. What we want to do is use the idea of object-oriented programming and encapsulate some values into an object. Fine. What we have here is a simple class called point. It has 2 values, x and y, both of which are doubles. But to do that, I have to write all this code. I have to create a class called point, then I have to specify that it's got 2 instance fields, double x, double y, which I'll make final and private. Then I need a constructor, which is going to take 2 parameters, double x and double y, and all I'm going to do in the constructor is just assign the values of x and y to the instance fields x and y. And then I need 2 methods which are going to return the values of x and y. Great. 14 lines of code to essentially make a tuple. I've always thought with Java that we should have had a tuple class in the standard class libraries. And I did talk to Brian Gertz about this, and I said, why don't we have a tuple? Why don't you add tuple? It wouldn't be particularly hard to do that, would it? And he said, yes, we could add tuple, but then you'd want a triple, and then you'd want a quadruple, and then you want 5. And where do we stop in terms of a class that stores simple data types? What the developers did then was they said, okay, rather than using a tuple class and a triple class and so on, let's add a different way of doing that and make it more general. And that is the idea of records. So records are a special form of class in the same way that enumeration is a slightly special form of class. What we now do is, rather than defining a whole class with all of the body and all of the functionality there, we simply say, let's define a record. So we say record, then the name of the record we want, point. We'll use the same syntax that we have for the constructor of a class, and we'll say what variables, what instance fields we want this to hold, double X and double Y. And then because it is still a form of class, we can specify a body of that using the braces, but we can put those on the same line. What that does is reduce those 14 lines of code that we had to 1 line of code. And again, it doesn't lose any of the readability. We can still see that in this case, it's a point. It stores 2 values, double X and double Y. When I create a record called point, I pass 2 values to it. They get stored in there. I call X as a method. I call Y as a method to get the values out again. I can see exactly what's going on. Now, records, like I said, are classes, which means we can use generics. I could create a record called anything, and I can provide to that a generic type T, and I can say that the thing that I want to store in that record can be of type T. So I can make my record generic. I can have records that store different types of object. We can, if we want to, add more functionality to the body of the record in the same way that we would any other class. Here I've got a record called circle, which stores 1 value, which is the radius. I want to have a method in there which is going to calculate the area of the circle. To do that, I define my own method called area, which returns double, and within that I'm going to calculate the area using pi r squared. What I also want to do here, I could have other methods that are going to calculate maybe the circumference of the circle, and so I need pi to be available. I can add that as an instance field so long as it's static. Because I'm defining the value of pi, it's fixed, I can have a static instance field called pi and have a value associated with it. What I can't do is add an instance field if it's not in the record declaration. Because I've declared circle as only having 1 instance field radius, what I can't then do is put inside the definition of circle another instance field called diameter, for example. That won't work. So static instance fields are fine, but other instance fields that are not in the record declaration won't work. There are some additional things that you need to know about records. First of those is that all records have a base class of java.lang.record, meaning that you cannot define a record which extends another class. It already extends record, so we don't have multiple inheritance in Java. You can't then extend something else. However, because we can implement interfaces as well, you can have a record which implements as many interfaces as you like, and you can provide the implementation of the necessary methods within those interfaces. Next thing to know is that a record is implicitly final, meaning that you can't then subclass it into something else. So the idea of records is all about simple data types. You don't want to be able to extend another class, that would be complicated. You don't want to be able to extend the record further, that would be complicated. It's simple. So records are implicitly final. If you really want to add the final modifier to the definition, you can, but it's irrelevant. It's already going to be final. The standard methods equals hash code and toString. There will be implementations of these provided by the compiler, because the compiler essentially is generating all of the code that we saw on the previous slide. It will also generate standard methods for equals hash code and toString. But if you want to, you can override those and provide your own implementations in the body of the record. One other thing to say about records in terms of the data that's stored there, it uses shallow immutability. All of the instance fields that you define in a record declaration will be final. That means that the reference will be final, but clearly if you've got a reference to, let's say, a color object, then the reference to the color object is final, but the object itself, you can change values internally in that. So it's not, the immutability is only in the references from the record itself. Another point here, records do not follow the Java bean pattern. This was one of those things that got discussed a lot during the development of this particular feature. And the designers eventually decided, rather than using get followed by the name of the variable, get X or get Y, they would use just the name of the variable, X or Y. Now this is fine, except that sometimes it can kind of cause a few problems. If you look at things like JAX-B, Java API for XML binding, that expects the use of the beam pattern for things that you pass to that. And when people try to use records with that, they don't work because, of course, it's expecting to use getX rather than X. There is a solution to this, which I don't think is necessarily the most elegant solution, but it is a solution, which is to go, okay, well, rather than calling my value X, I'll call it getX. And rather than calling it Y, I'll call it getY. And that way, when the accessor methods are generated, because they're the same as the name of the variable, they will be getX and getY, and then things will work. So if you really must, you can do that. But again, not really to be recommended. Constructors in records. Often when you have a class, you might want to add some additional logic in terms of what the constructor does. And the designers of records provided a couple of different ways of doing this. First is to use the canonical constructor, essentially the same constructor that you would have in a normal class. I've got a record here called T-Rex, and I'm declaring that it contains both an int x and an int y. Then I need to have some extra logic in my constructor to test whether x is less than y. Using the canonical constructor, I define a constructor in the same way that I do in normal class. So public T-Rex takes int x, takes int y, do the test if x is less than y, and then I have to explicitly assign the values of x and y to the instance fields. This is not really ideal because, of course, now we're sort of getting away from that ability to eliminate a lot of the boilerplate code we had before. We've brought boilerplate code back in again. To get around that, the designers added the idea of a compact constructor. Again, if I take my record here called range, takes two values, low and high, and when I define the compact constructor, I don't need to specify parameters to be passed to the constructor. Makes sense because, of course, if we look at the line above, the compiler is already going to know that we're going to be passing in two values, low and high. We then add the extra logic we need to test if low is greater than high, throw an illegal argument exception if it is, and then we don't have to explicitly set the assignment of the values because, again, the compiler can do that for us. This is good because now all we need is our own logic. We've avoided that extra boilerplate code as well. There is one thing to be aware of here, which is I've decided to throw an exception from that constructor. I am limited in that I can only throw an unchecked exception from the compact constructor. There is no way to say public range throws my exception. You can only use an unchecked exception, so illegal argument exception, null pointer exception, or whatever you want to do, but it's unchecked rather than checked. If you really do want to throw an exception, checked exception from your constructor, again, there is a kind of sneaky way of doing this, which is that I've got my T-Rex example here. I've got int x and int y. I define another constructor, so I'm overriding constructor with one that takes three arguments, in this case, int x, int y, and int z. Now, I did say that we can't add an instance field to a record that isn't in the declaration, which I'm still not doing because even though I'm passing z as a parameter, I'm not using it anywhere, so that will work. And then I can have a throws clause associated with that. So I can throw T-Rex exception. The one thing I have to remember is that I must call the standard constructor with the two values x and y so that they do get assigned, and then I have to then do my test, and then I can throw my checked exception. The important thing here is that the constructor signature must be different to the canonical one. So it must have more arguments than the standard constructor. We can also provide a default constructor if you really want to. You could do this. You could have public T-Rex with no arguments, default constructor, and then you would have to provide the values for that. So all of those records would have the same value. Again, I'm not totally sure how much benefit this is and how many people would actually use that, but technically it's possible. You can do that. Instance of. This again is something that's been in Java right from the very beginning. Java is an object-oriented language, and what that means is that we can have type hierarchies. Within that, we can pass objects of a higher type, and then we can potentially want to test to see if that object is of a specific subtype. To do that, we use instance of. In this example here, I say if obj instance of string. And then the first thing that I'm going to have to do is, if I want to use obj as a string, which I most likely am going to want to do, then I have to create a new variable called s of type string, and I have to assign to that the reference obj and do an explicit cast to tell the compiler that I want to cast it to a string. Now, if you look at that, that's kind of redundant. The compiler should be able to do this for us. We should have to do all of that extra work. And in JDK 14, we now have pattern matching for instance of. Pattern matching as a construct in programming languages has been around since the 1960s, and it covers quite a wide range of different uses. In this particular case, what we're doing is pattern matching for a type. Now, what we do is we say if obj instance of string, so that's our pattern that we're looking for, and then we specify a pattern variable, s, which the compiler is going to know is going to be the one that we want to use as a string. So it will do the extra line of code that we've removed here. It will create s as a string reference. It will then assign to that obj in a way that we can reference it as a string. Now, in the true branch of that if statement, because we know that we do have a string, the scope of s is valid, so we can call s.length and print it out. In the false branch, we know we don't have a string reference as obj, and so s, the scope, will not be valid. We can't use it, and the compiler would generate an error. We can be slightly more sophisticated with this, and we can say if obj instance of string s, and then use an AND operator, and then test to see if the length of s is greater than 0. This will work because we know that with the AND operator, we always evaluate the left-hand side of the operator, and only if that equates to true will we evaluate the right-hand side. That means that if we evaluate the left-hand side, we know we have a string, scope of s is valid, and then when we evaluate the right-hand side, we can test the length of s against 0. If we were to use an OR operator, that won't work. It's a compiler error. Again, we know that we always evaluate the left-hand side of the operator, but only if it evaluates to false will we evaluate the right-hand side. If it evaluates to false, we don't have a string, the scope of s is not valid on the right-hand side, and therefore we can't call length on it. It would be wrong. That will be a compiler error, and it won't work. We need to be a little bit aware of how scoping of our pattern variables works, because it uses what's called flow scoping. In this case, I can actually invert the test, and I can say if not O instance of string, and then use the variable s, return from my method, which means that if I don't have a string, I return from the method. After that, because I do have a string, the scope of s is now valid up until I return from that method. So it's just something to be a little bit aware of. And then there's one last thing I just want to sort of mention, which is this. And so the question is, will this work? If I create an object called s and instantiate a new object, then I say if s instance of string s, so I'm using s to reference object and I'm using s as a pattern variable, print out the length of the string, calling s.length. Otherwise, print out no string. Now, normally, I've been fortunate the last week I've been actually doing presentations like this in front of a live audience, so I can actually ask people and people put their hands up. And it's interesting to ask, who thinks this will work? Who thinks this won't work? And the answer is that if you put that into a file and you run Java-C on it, or if you put it into your IDE and you try and compile it, it will fail. It will fail because the compiler will say, well, hang on, s is already in use as the reference to the object. So when you try to use it as a pattern variable as your string, then no, you can't do that. However, if you run that exact same code in JShell, it will work, and it will actually print out no string, which I find very odd, because I thought that JShell actually simply built on top of Java-C, so it used Java-C as the compiler. Clearly, there's something there that I don't know what's going on, so I'm going to have to dig into that at some point to find out what's actually happening. Text blocks. We now have a second preview of text blocks. They were introduced as a preview feature in JDK 13. Now we have a second preview that introduces 2 new escape sequences. And again, this is based on feedback from developers about how they worked in the first preview release. What they've done is add the idea of enabling you to put a backslash at the end of a line to indicate a continuation. This is good because that solves that problem of the extra blank line if we want to introduce some intentional indentation. If I move the closing 3 double quotes onto the next line, push them over to the left to indicate that I need that extra space, by putting a backslash at the end of the last line, I then don't get the extra blank line that I had before. So this is nice. The other thing they did was to address that problem of stripping out trailing spaces. They now allow you to use a \s to say these spaces I actually want to keep at the end of that line before the new line that gets inserted in there. Again, solves the problem that we had before. So it's useful. Again, it's a good way of using preview features to allow where people say, "Oh, hang on, we want that to work in a slightly different way," and they've addressed the problem, and it's now included rather than having to try and change something that's a final feature. Helpful null pointer exception. This is probably my favorite feature from the last couple of years. I think it's probably fair to say that if you've ever written more than a few dozen lines of Java code, you will have had a null pointer exception at some point. And the problem we have here is if we do something like this, we chain together some references. We say a.b.c.i equals 99. We run our code and we get this. We get exception in thread main, null pointer exception on line 5. Wonderful. So we look at line 5 and we say, okay, where's the null pointer exception coming from? Is it A is null, so we can't reference B? Is it B that's null, so we can't reference C? Or is it C that's null, so we can't reference I? Then we have to use the debugger. We have to, test, see which thing is null, and then it makes life hard for us. In JDK 14, we now have the idea of an exception message which tells us what the problem is. Great. Null pointer exception cannot read field C because a.b is null. Now we know that a.b is null. We can go back and look at our code and where did a.b come from? Oh, that's why we haven't assigned a value to it, blah, blah, blah. Great. The only downside with this particular feature, at least in JDK 14, is you have to enable it. You have to enable it with the very catchy, very easy to remember command line flag -XX plus show code details in exception messages. Why? I mean, why do you have to enable this? How many people are going to parse null pointer exception messages and then suddenly get confused because there's an extra line in there? Almost nobody, I would have thought. In terms of APIs, one of the kind of bigger projects that's going on in Java at the moment is called Project Panama. Project Panama is about replacing JNI. How can we interact with native code? And that consists of 2 distinct sort of parts. The first of those is what I'm going to talk about here, which is foreign memory access. It's the ability to access memory outside of the heap. If you think about languages like C and C++, you have explicit pointers. So you can simply reference an address in memory and do whatever you want to do with it. That's all good, but it is actually somewhat more error prone than the way we do things with implicit references in Java. But there are times when you might want to access memory outside of the heap, and this API does that in a more simple and controlled way. What we've got are a number of classes that you can use to do this. So for example, we have a memory segment. Memory segment models a contiguous area of memory. So you point to an area of memory and then you can use that in whatever way you want to. You then have an abstraction which is a memory address. So you've got your memory segment. If you want to point at a particular place in that, you can use a memory address as a way of referencing the actual specific address. And then you can also have the idea of a memory layout, which is where you want to be able to describe a memory segment. So a memory segment is just an area of memory. Maybe you want to describe it as something that holds particular type objects, and we'll see an example of that in a moment. Very simple idea here. If I wanted to do that, let's say I simply want to have an area of memory of at least 100 bytes, and I want to be able to store some integers into that. So to do that, I'll create a new memory segment, and I'll allocate in native memory 100 bytes. It's kind of like malloc. Having done that, I can then produce a loop which goes from 0 to 25 and will then put integers into that segment using memory access set in that offset, and we have to calculate the offset using the knowledge that we have of the fact that an integer is 4 bytes in size, so we do 4 bytes, 4 bytes, 4 bytes, and so on. Obviously that's one way of doing it, but it could be better. And that's where we can get into the idea of using memory layouts and var handles. What I want now is to define a memory layout which is going to hold a sequence of integers. So I create a sequence layout and call it int array layout. So that's going to be a memory layout which is a sequence of 25 of something, and the somethings that I want to store in there are things which have 32 bits. So they are our integers, and the order for those bytes, is going to be native order. Native order means that whichever the hardware that the machine is running on uses, so whether it's least significant byte or most significant byte, we don't care, just use whichever one's appropriate to that machine. If you did want to store them in a particular order, you could specify a byte order of most significant byte or least significant byte. Having created our sequence layout where how we want to store information, we then create a var handle to that using the sequence elements that we have, and then we can say, right, we want to use that var handle to be able to write things into the sequence that we've created. Then we create a memory segment the same way as before. So we have our allocate, but we don't say what the size of that is, because the size will be calculated as a sequence of 25 32-bit values, therefore 100 bytes. And then we can simply go, right, we want to do the same storing thing that we did before, where we're going to store values into that, but this time we don't have to explicitly calculate the offset because we've defined the layout of the area of memory we're going to use. Then we simply say store value, then store next value, and so on, and everything will be handled for us. So it is I'm going to say simpler. It's a simple way of referencing native memory, although as you can see, it's not immediately, it's not totally straightforward and uncomplicated. There's a little bit of work to be done, but it does give you that ability to control very carefully how you want to interact with native memory. JDK 15. Now, JDK 15, Java as a language has inheritance. We've already kind of covered this in some other things. And we can have a class hierarchy like this, where we've got a simple shape as a superclass, and then 3 subclasses, triangle, square, and pentagon. The thing about this is that we don't have any control. Well, we have very limited control over how shape can be subclassed, meaning that we can either specify it as final, meaning that nobody can subclass from it, or if we don't mark it as final, any other class can subclass shape. The drawback to that is that if I'm writing this code and I create shape, I create triangle, square, and pentagon, fine. And then one of my colleagues, we're working on a very large project, he sees that I've created this shape class and he says, that looks good, I'm going to use that. So he subclasses shape, fine. I come along and I think, actually I need to change the way shape works in terms of my type hierarchy. So I'll make some changes to shape, and because I know what changes I've made, triangle, square, and pentagon will still work in the way that expected. The problem is that my colleague who has used shape, unless they're checking to see that a new version has been checked in, they might then suddenly find that shapes works in a different way, and that affects the way that their subclass works, and it causes problems. What we'd like to be able to do is to restrict access to a particular class, so that if my colleague really wanted to use it, he could come to me and I'd say, oh, okay, yes, I'll add you, and then I know that you're using it, so if I make changes, I can let you know about it and we can keep everything in sync. This is where sealed classes come in. So a sealed class does exactly what we want it to. It allows us to control which classes can subclass a particular class. And you can think of final as being the ultimate sealed class, meaning that nobody can therefore subclass it. Interesting thing here is when I saw this and I read the description, it also applies to interfaces. So it's sealed classes and sealed interfaces. And I thought to myself, why did they call it sealed classes? Why didn't they call it sealed types? Because then that would apply to both classes and interfaces. And I tweeted about this, and one of the Oracle people came back to me and said, look at this. And it turns out that I didn't know that an interface technically is a class. So I learned something new there. So because an interface is technically a class, they decided to call it sealed classes. In terms of how this works is that all the classes involved must be relatively close together. They either have to be in the same package or they have to be in the same module. And the way that it works is by changing the way that you define your sealed class. We do that firstly with a modifier. So we say public sealed class shape, and then we add a permits clause which lists a number of classes which are allowed to subclass shape. And the important thing about this straight away is that none of those classes have to exist at that time. All we're saying is that those three classes, triangle, square, and pentagon, can, if we provide them, subclass shape. But it isn't saying that all those three classes have to be there as well. That then allows us to have the same hierarchy that we had before. So we've got our shape, we've got our triangle, our square, and pentagon, everything works. If my colleague comes along and says, oh, I like shape, I want to create a new subclass of that called circle, then it will not compile. The compiler will say, no, shape doesn't have circle in the permits clause, therefore you're not allowed to subclass it, and it won't compile. In terms of the subclasses of a sealed class, all of them must explicitly state their inheritance capabilities. And there are three ways of doing that. The first is that we could continue to make the subclass sealed. Take triangle as our example. We could say public sealed class triangle, and then specify another permits clause that both equilateral and isosceles could be subclasses of triangle, but anything else would be a compile error. And we extend shape. The second thing that we can do is to prevent any further subclassing in the normal way that we would do, and mark, in this case, the square class as being final. That way, nobody can then further subclass square. And the third thing that we can do is we can make that into an unsealed class. We can remove the sealed aspect of it. We can open it. We do that by using a different modifier, and we say public non-sealed class pentagon extend shape. This was quite interesting in terms of the development of Java, because there was a lot of discussion that went on about whether we should include the idea of hyphenated keywords in Java. And the upshot of that, the end of the discussion, was that yes, we should, because it means that the language can be evolved much more easily by having access to more keywords. Now, it's quite important to understand here that in this situation, non-sealed, and in fact sealed as well, these are contextual keywords. A contextual keyword is one that only behaves as a keyword in a specific place. Now, public and class are both reserved words in Java. You can't have a variable called public, you can't have a variable called class, but you can have a variable called sealed. You can't have a variable called non-sealed because hyphens can't be used in variable names. And one of the things that came up as quite interesting about this, with the whole idea of hyphenated keywords, is that this is still valid Java code. You can say sealed equals non-sealed. And you go, well, how is that then? And the answer is because you could say int non equals 4, int sealed equals 2, and therefore sealed equals non 4 minus 2. So sealed becomes 2. It's just one of those things that I like to put up on my slides because it's kind of interesting to see that you can do some kind of strange things like this. Records. So we saw records introduced in JDK 14. Now in JDK 15, we have another preview of that. So there's still, again, possibility of making changes. A couple of things that they changed there. First was that they made the fields of record really final. So I said that we have shallow immutability in that we can't change the value of the fields in a record because they're marked as final, unless, of course, we use reflection. So reflection allows you to still change the value of a final field. Now, with our second preview of records, they've enforced that you cannot change the fields in a record even with reflection. So you get an illegal access exception thrown if you try to do that. The other thing they did, which is a minor thing, is that they prohibited native methods from records, which were allowed before, and they said that could introduce behavior dependent on an external state. Like I say, records are all about data classes, simple data classes. The other thing they did in the second preview of records was to allow local records, and this I think is a really good thing. So what this does is allow you to include a record so that it's only used within a particular method. Rather than having to define it across your whole application, you say, I want to use this just in this method, and it makes life easier in terms of not having, again, type pollution and stuff like that. In my example here, what I've got is a method that takes a list of people who sell things for me and a month that I'm interested in. I'm then going to create a local record called sales, and that takes two values, a seller and a value for how much they sold. So it's a tuple. Obviously, I could solve this problem in a number of different ways, but by using a local record, I can make this really succinct code. What I do here is I say, okay, take my sellers, create a stream from that, which gives me a stream of seller objects. I pass that into map and map that into a stream of sales local records using the seller from the input stream and then also calculating how much they sold in the month that I'm interested in and put that into the record as well. I now have a stream of local records, sales, and I pass that into sorted, which will use the comparison of the amount that the sellers sold. So I order them by how much they sold in that month. That way my output, my stream, is now an ordered stream of local sales records ordered by how much the person sold. I map that back into the sellers by simply extracting the seller from each of the local sales record objects. That's then still ordered by how much they sold in that month. I then collect that into the list and I've got the result that I want. So I've got my sellers ordered by how much they sold in a given month. Like I say, we could do it in different ways, but this for me is really nice because it allows us to do some very simple things in terms of having simple data classes in our streams. Helpful null pointer exception. Yay, they figured out that it didn't make sense to have that silly command line flag that turn it on. So now it's turned on by default. Wonderful. JDK 16. JDK 16 didn't actually introduce any new language features into the platform, but what it did do was make a couple of them final. So there's no more changes being made to those. Records are now final in JDK 16. So we had some changes in JDK 15, no changes in JDK 16. Pattern matching for instance of, that also became final, but they did make two minor changes to the previous iterations. First of those was that pattern variables, the ones that we use like string s, are no longer explicitly final. In the past they were. What they've decided is that you can actually change the value of it, which I think actually makes sense. And then the other thing they said was it's a compile time error to compare an expression of type S against a pattern of type T, where S is a subtype of T. And you have to read that a couple of times, but if I show you an example, it's a little easier. I've got a method that takes a rectangle as a parameter. If I then do if r instance of rectangle rec, print out what the rectangle is. Well, that's a redundant test, because if I'm passing a rectangle in, then it's always going to be an instance of rectangle. So it's an irrelevant test, it's always going to be true. And the compiler will now give you an error. If you use JShell, like I did, it'll say rectangle is a subtype of expression type rectangle, and it won't let you do that. A couple of things in the API side of things. Again, a small change to streams. They introduced a toList terminal method. This is really sensible. Because often when we're using streams, we collect into a list. And to do that, we would use collect, and then we'd use collectors.toList. Now there is a terminal operation, which means we can just do, instead of collectors.toList, we do toList. That's just saving a bit of typing. So again, one of those little changes which I think is really quite useful. Another thing they did in JDK 16 related to the period of day. So the way that you can specify the period of day in the past was simply as AM or PM, before midday or after midday. And now we've got a more descriptive way of defining that. If we do date time formatter of pattern, and then they use capital B, because clearly they're running out of letters, because capital B has nothing to do with period of day, and then do format local time now, what you'll see is in the afternoon. So you get in the morning, in the afternoon, in the evening, at night. There's a variety of different strings that are used to describe what the time of day is. A bigger set of API changes is the vector API. And again, this is an incubator module, not to be confused with the vector collection class, which was, way back in 1.2. Vector API is all about expressing computations that you want to do in a way that can then be turned into vector processing at the chip level, the processor level. What we find is that modern processors have single instruction, multiple data instructions. It allows you to load up a number of elements and have them processed in parallel. Ideally, we wouldn't need to do this because the compiler would be smart enough to figure that out for us, but there are often many situations where the compiler won't spot things and we can make it explicit. What this does is, if we think about processing a number of elements in an array, what we typically do is apply the same operation to each of those in turn. We do a loop. And if we want to add 2 to those, we'd go take the first element, add 2 to it, take the second element, add 2 to it, third element, fourth element. So it's a loop, it's iteration. But that's taking us 4 operations to do the same, to do that workload. With a vector, we have a very wide register that can hold multiple elements of an array. We load up our first 4 elements into this wide register. If we're using integers, then we're going to have a 128-bit wide register. And then what we can do is use a special instruction to say, do the same thing to each of those elements in a single clock cycle. So we're saying add 2 to each of those, and rather than having to do it as 4 instructions, we do it as 1 instruction, 4 things in parallel. Take a simple code example. What I'm doing here is I'm saying take 2 arrays and only add the value of the second array to the first array if the second array is even. And like I said, the problem is that the compiler will not recognize this as something that can have vector operations applied to it. The problem with this, from a compiler's perspective, is the test, the if statement, which looks at if we have a particular situation. And that's what causes the compiler to get a bit confused. Not confused, but not apply the right optimization. So we look at what happens here. We see that without the vector API, we're doing loop unrolling. So we're saying, okay, let's do 2 minutes left. Okay. Oh, wow. Okay, that's a little less than I thought. Okay, I'm going to skip past the vector API part then, because that's not quite as interesting as the JDK 17. So we'll just talk a little bit about JDK 17. Pattern matching for switch. This again is pattern matching being included into the language. If you look at switch, then we had the idea of only certain types can be switched on: integral values, strings, and enumerations. Now what we've done is extend that to type patterns. And we can do something like this, where we can say type tester on object O, switch on O, and then have cases for the different types. First of those, we can test for a null if we need to. We can do string S and then use S on the right-hand side, color C, we can use c.getRGB on the right-hand side. We can't have a case for a primitive, but we can have a case for a primitive array. So int array, we can print out the length. Things have to be complete. So if I have a switch on an object and I only have cases for string S and integer I, the compiler will reject that, because what happens if I pass a float? In that case, we have to add a default case to it, and we can have situations where we don't have to have a default. So if I use my shape from earlier, if I switch on shape, I can have case triangle, case square, case pentagon, case shape, and the compiler will say, yes, that is a complete set of types. Just to finish then, guarded patterns as well. So you can use triangle T and t.area greater than 25, same as we had with pattern matching for instance of, and then because that might not pass the test of T being greater than 25, then we also have to have a case for triangle T. Okay, so since I expected to have another 10 minutes, I am going to finish my presentation there. Just wind through. I'll just do the conclude and summary slide there. So essentially, 6 months release cycle is working really well. Many new features added to the JDK since JDK 9. There's some other big projects that are coming through as well. Project Loom, Project Valhalla, Panama, talked a little bit about there. And obviously OpenJDK is developing the Java platform in the open, and you have many more choices for your Java runtime. And I would obviously tell you to consider looking at Azul, our platform core for standard builds of OpenJDK, and we have a high performance JVM for Platform Prime. And so that's the end of the presentation. I shall be going over to the Rocket platform to answer questions, I believe.
Yes, thank you so much, Simon. Thank you for your presentation. I want to invite you to our discussion table to speak with our participants. Maybe they have a lot of questions after this deep dive during 2 hours. Thank you
Okay,
a lot.
thank you.